Hello, everybody. How y'all doing? We're actually missing one of our presenters. They're supposed to be doing this presentation with us today. Their focus is on solar, but we're gonna still try and do the best that we can, know some portions of the slides as best as we can. So we just wanted to preface it first, and then just to let you guys know. Thank you.
Okay. So good afternoon, everyone. We are Ashley, Uche, Quentin, and Oscar. We are the Energy Transition Roadmap team. We're going to present to you our research. And so we start with the problem. Problem is that as a world, 77% of the energy that we consume comes from fossil fuels here. This information comes from the Energy Institute, and we understand the issues from the carbon emissions perspective that this reliance on fossil fuels has for us, but our focus is on their effect with regards to our energy supply, our sustainability to actually keep consuming so much of these sources. And so we first started by looking at other projections. This is also from the Energy Institute. And what we see here is basically a graph of the estimated years remaining for each of the fossil fuel sources. You have coal, oil, and gas, the number of years remaining. And this is basically done using the known reserves and taking into account the amount of fossil fuels that we extract. So as of right now, the Energy Institute basically is stating that we will run out of oil and gas by the end of the century, even less. So we took this chance to look into it and really see if indeed fossil fuels will run out in the near future, or if there is a possibility to actually other energy sources to contribute to our energy consumption and offload our dependence from fossil fuels. And okay, so the first thing we did was we looked into the US, right? So this big picture world, now we go into the US. With regards to the US, what we saw is that wind and solar energy grew massive amounts, right? If we look at the compound annual growth rate, which is the CAGR, which is just a measure of the year-over-year growth in a specific time period, we see 21% for wind, solar 34%. We have a massive growth. But if we shift our focus to the energy consumption breakdown, this for 2022, this is from the US Energy Information Administration. Even then, with these high growths, wind and solar only account for 6% of the energy we consume. And this is taking into account the last 2 decades of growth, with nuclear and hydropower having grown nothing, or even nuclear decreasing. And so, most alarmingly, is actually the dependence that we have here in this country on fossil fuels. And now, different estimates will say between 80% to 86%. This is 86% reliance on fossil fuels for any consumption. So the first thing we're going to do is actually go into the alternative sources of energy, so nuclear, hydro, wind, solar, and we're going to look at if their growth and project them in the future. So solar will start now. This is the part that we're missing the member.
Right, so just to give a brief introduction here, the way that we decided to analyze wind and solar was to create a table that basically ranks their adoption potential. So first we looked at wind and solar together and we said, what's the overall importance of this resource to be able to contribute as an alternative? And we gave it an importance score of 1 through 3. 3 meaning that this is really important. It needs to be cost effective, such as LCOE, or levelized cost of energy. Then we rated wind and solar individually based on their performance. So they received a score 1 through 10 that basically explained how well they excelled in that area. If it was very cost effective, it would receive a 10. If it had bad job creation, it would receive a 1. So essentially going through these factors for solar, we ended up giving it a score of 138. And then this graph here shows a projection of what we expect solar electricity to produce by the year 2030 for the US. On the left is our projection based on the Department of Energy's goals for 2030, which are usually set in place by the government and also what technology will allow. On the right is a projection set in place by the Energy Institute, the EIA, which is based on decarbonization goals. So the discrepancy in this graph, as you can see here, there's a higher compound annual growth rate, or CAGR, in the right, because what we estimate is possible for these technologies is not necessarily what the decarbonization goals have in mind. So here, we've actually adopted the ambitious growth model of the EIA to see if this is what we need to scale solar at in order to be cost competitive with other conventional resources. So you can see here that production is estimated to be roughly 3,000 terawatt hours for solar in the end. So if we do the same analysis for wind, we can see that it has an adoption potential of 110. And if I go into more about why this is true, we can say that wind is a pretty cost competitive resource to be utilizing today. Onshore wind is roughly 50% lower than other fossil fuel resources, while offshore wind is a bit more expensive. In the future, it is expected to be 28% lower than the price of natural gas today. Advances in technology have increased the capacity factor of wind turbines and enabled us to build turbines with longer blades and smaller generators. By producing power at a lower specific power factor, we're able to more often maximize these generators and achieve a higher capacity factor. Producing a more stable power supply this way makes the cost of electricity cheaper and also enables us to place wind turbines in locations that don't receive as much wind. One of the biggest challenges moving forward is the high price of materials for wind turbines. Copper and steel are very expensive and in recent years have seen 2 to 3-fold increases in price. This has led developers to not be able to manufacture affordably, and not being able to do so has also prevented them from receiving important tax credits from the Inflation Reduction Act, which requires them to domestically manufacture their materials. So not receiving these bonuses and the sum of these factors leads me to give wind a score of 100. And here we can see that through our projection for wind energy production, it should reach 20% of overall electricity production by 2030. We expect a 7% compound annual growth rate for wind, and that will require 5% growth for onshore wind. But overall, offshore wind will need to grow 34%. This is a significant amount. Currently, we only have 110 megawatts of offshore wind installed, or 0.11 of that 30 gigawatt goal for 2030. Significant investments will need to be made not only in turbines, but also in how do we install them. We need to build wind turbine installation vessels, the first of which is just being finished in the US today. It's taken 4 years to build and roughly $800 million. We'll need 4 to 6 of these in order to reach our goals by 2030. Otherwise, foreign developers have to operate from their faraway ports in places like Europe and use offshore barges due to legislation that prevents foreign ships from operating in US ports. So we can see this is a pretty big challenge for offshore wind. However, like we showed with solar, there are challenges or differences related to what decarbonization goals have in mind set by the EIA. And we can see here that there's a 3% higher CAGR when we compare what the output of electricity should be by 2030. So again, we've actually adopted this model to say, is this the rate that we need to grow at in order to reach our goals? And we can see that with this growth, wind will only account for 7% of our overall energy consumption by 2050, even as we explode our growth from now until 2030 and steadily as the industry develops, continue to grow until 2050. And also, the way that we created this graph, just to preface, is that we compared the output from resources such as wind and solar to the input of primary energy inputs or resources such as fossil fuels. And we took into account their thermal inefficiency and multiplied by a factor of 2.5 in order to compare both as thermally inefficient inputs in terms of terawatt hours. So looking forward, we can talk a little bit about nuclear.
I just have one slide for nuclear because this slide essentially defines our whole point of view for this roadmap. Essentially, the US is the largest nuclear energy producer in the world. It has 94 reactors. France has 56. China has 55. And so it produces about 30% of the world's nuclear energy. And in this graph here on the left, you can see that since 1965, you see a clear growth. But then you see something really interesting happening in 2018-19. And this happens because wind and solar actually become much more economically viable as energy production sources. They're cheaper to make, they're cheaper to maintain. You actually need less people. And there's also the whole safety aspect. which comes in play. And this is really also a definition of how the US policymakers have tried to orient this kind of resilience energy production in the US, let's say. And so it would really be a bad look if you would essentially extract your uranium and plutonium from Russia, Kazakhstan, or Uzbekistan. Can also do it from Canada or Australia. But this is really kind of a willingness from the policymakers in Washington, and they wanted to push harder, let's say, on wind and solar. And so this is a consequence of this, but also a consequence on the engineering. And in our roadmap, we can predict much better how much one wind turbine produces, how much one solar panel produces. And this is why we've chosen to orient this roadmap, this discussion, and these results more on solar and wind. However, I could sell you SMRs and fusion and tell you that it's going to revolutionize the world. But truth is, we don't really know how they perform. Even experts are kind of hesitant on what you can get out of these. And so this is why we essentially decided to focus on what we know and what we could predict more easily. And so this kind of tells you what's the state of the US, what's potentially not going to grow in fission. But however, Oscar has done some predictions on fission that he will present to you after.
So now let's talk about hydropower, right? Like Quentin already said, similar to nuclear, we don't necessarily see it as something that is definitely going to be a focus in the future. In this case, we're still going to talk about it and also the reason as to why. Mainly, as of right now, 3% of the energy consumed in the US is hydropower, which is more than solar and biofuels combined. Along with that, there's a case where previously in the US, it was actually, well, prior to 2019, in terms of renewable energy in sector of our sections or the amount of energy produced, it was the most in the US up until it was surpassed by wind in 2019. And as a result, well, now speaking on as to why it's not going to be necessary for the future, there's actually expected to be a decline in energy generation from hydropower, mainly due to reasons as in we've already used most of the suitable locations in the US. If you were to look at the graph on the right, you can see a lot definitely in the, I know my directions, northwest. Yes, you can see there's a cluster of them. And as a result, the largest amounts of energy that can be generated in the US have been used, along with the technology being simple. Relatively, how much can we actually develop it in comparison to solar and wind? As you can see in that previous presentation when they had a lot of stuff here, it would look nice. So that's it for at least hydropower for now. And now we're going to speak more, putting back everything together. We have solar, we have wind, we have nuclear, we have hydro, right? But now let's go back to fossil fuels. We have, this is a graph that actually shows the projections in the future, 1% going down or negative 1% total growth, so a decline. That's including coal, gas, and oil. Now I'm going to pass it back to Oscar. That's going to kind of put all these things together and put it more into perspective.
Thank you. And so really this graph that you have here to your left is the compilation of all of the energy sources that we've mentioned, right? The yellow is what just Uche presented in terms of fossil fuels. Then these are the projections to 2050 for each energy source that we've talked about, actually with wind and solar, Quentin with nuclear, hydropower, Uche. So this is the projection that we've come up. And it is second by the EIA in terms of the overall growth expected, which is 18% to 2050. Now, it is still very obvious that we're going to rely highly on fossil fuels. There's 69% of our energy consumption will still come from fossil fuels by 2050. And the interesting thing is that this is not even a realistic growth scenario, because the truth is that as a world, and particularly the US, and in the last 2 decades specifically, has grown at about 1.9% year over year. This does not reflect that growth. And so if we account for it, and we assume that these are optimistic growth rates from the alternative energy sources and wind, solar, hydro tapering off, and nuclear as well, then we're going to need to go to the bank and ask for more fossil fuels in order to grow at the rate that we are projected to grow. And so this is an alarming fact. However, some may say, well, what about nuclear, right? Nuclear is very promising. Countries like France, you mentioned, are using it. Other countries are adopting it. Why aren't we doing it? What would happen if we did it? What would happen if right now we put all of our research to it. So we did a case study on this and said, okay, what would it take for us to have the same graph that we have here, right? So the same amount of growth rate here, but we need to grow of 1.9% year over year. This is what we expect. What would it take for nuclear to take up that amount such that fossil fuels still do not grow, right? It would require, these are very back of the envelope estimates, but they would require around $4.5 trillion, and that's a low bar. You can imagine it could be double, triple that, just to build about 1,500 nuclear reactors, which, as we know, there's less than 500 worldwide, which is an unrealistic fact to begin with. And this would be starting 2030, this growth, which is a little time to build a nuclear plant. You need decades for that. And even then, even in this unrealistic scenario, we would still depend mostly on fossil fuels in this country, 53% of our energy consumption from fossil fuels. And so there's only one question left, and that is how much time we have left. We keep going on this path. And so what we did here, this graph, what it is doing is that it is taking into account the reserves of fossil fuels we have, and what we're doing in terms of energy. And what we're doing is that we know that the US consumes 16% of the world's energy. And what we assumed here is that each country has their own portion of that consumption. It will remain the same. What we assume is what would happen if every country grew like the US? What if every country consumed like the US going forward at their own respective sizes? We find that indeed, like the Energy Institute predicted, we would run out of specifically oil and gas by the turn of the century. So a little after what the Energy Institute projected. And so to summarize, like we've presented, despite the explosive growth of wind, solar, even in an unrealistic scenario where nuclear fission would come in and contribute a lot of energy, even then, by 2050, we will still be highly reliable on fossil fuels. And in our realistic growth scenario, we predict that we will still rely about 80% of our energy consumption on fossil fuels, which will lead us to, if the rest of the world follows, probably to run out by the turn of the century. But really the takeaway message from our group is the following. We are on a path of unsustainable growth. And it is an issue that we will face in our lifetime. And it is an issue that most certainly our kids will face in their lifetime, if not their grandkids. And so we provide the diagnosis. And what we hope for is that the next energy transition team can actually start looking for answers to the question, how do we avoid disaster? Thank you.
So there's been a lot of news lately about geothermal, and Howell Power continues to see some investigation. Did you look at either of those sources?
We definitely did. There was for most of our research that we did last semester, it was focusing on looking at all historical portions, like the main sources of energy period, geothermal, even down to some new stuff like ocean wave energy conversion as well. And we incorporated a lot of that into our decision making as to what exactly to focus on. The biggest players seem to have definitely been solar, wind, nuclear, and hydropower as far as like the big contenders of how much we can actually produce. That was less on the theoretical side because it was all going to be based upon if the technology could be actually developed to the point of which where we can make some sort of impact. So we decided to focus on more the ones that are like the more current ones that we can see some technology and actually see a lot more growth in. And as a result, then we'll focus on what we were going to focus on for the presentation.
Thanks for meeting us.
Sure, of course.
So in your research, did you come across an indication as to what's driving or what specific product or industry is driving most of the problem, like the automotive industry, or where's the the biggest problem?
Remember the sectors.
Like sector strikes.
Yeah, the sectors.
I would say that our research, initially when we were given this project, we were asked, how should we go about it? And our first thought was, should we go into different sectors? Should we go into transportation? Should we go into heating? Should we go into electricity? But instead, we just focused on energy as a whole and different sources for providing energy and electricity, because we imagine, and other roadmaps imagine, that the grid in the future, or our power sources in the future, will become more electrified, more electric cars. How are we gonna have the power sources to provide for that? So we didn't necessarily take the time to diagnose maybe what we call now a climate change problem or an emissions problem. We chose to focus more on energy sources and how far they could take us for electrification.
Okay, thank you.
Due to time constraints, these are all the questions we could accept. So could we please give a round of applause to Team 54?